This work develops a scalable simulation framework and demonstrates complex dynamic motions for a 5-actuator piezoelectric soft robot. The robot consists of 5 piezoelectric actuators bonded to a single steel foil. We attach high-friction films on the underside at the two ends. Each actuator will bend up or down depending on the applied voltages. We develop a simulation framework of the robot to model the piezoelectric actuator as multiple motor link elements. The motor link model is then integrated into a physics-based rigid robot simulator Piezoelectric to solve dynamics including the effects of gravity and friction. This simulation framework is validated against experiments. It's first tested in a single actuator cantilever. Experiment and simulation results are played at the same time for comparison. Good agreement is observed in time and frequency domains. The actuator bends down and up with swaying voltage. We plot oscillation amplitude at varying driving frequencies. The resonant peak amplitude is 60 mm at 23 Hz. Moreover, the robot jumps in place when the middle 3 actuators are cycled at 14 Hz, again demonstrating close agreement between experiments and simulations. The robot jumps completely off the ground. We plot the jumping head sweeping the driving frequency. The robot starts to jump at 5 Hz, and the jumping head maximizes at 14 Hz for 7.5 mm. We further explore robot horizontal motion by changing the voltage waveform. A forward-leaping motion is observed at 13 Hz. The model reproduces very complex behavior of the robot. Sweeping the driving frequency changes the direction of motion. The simulator shows good qualitative agreement with experiments. It captures forward motion at less than 3 Hz. The robot moves to the other direction at 8 Hz. Highest velocity is at 14 Hz.